Yes. Yes. Okay. So maybe we can start. So thanks to both of you for showing up. So now I don't have to give the tutorial to an empty class. Um, but I think I'll try to do this a bit fast so that we don't take too much of your time. So I'm going to do question 2, 3, 4, and then question 1 in that order. So I'll start with the minimization question. So in this question, this was kind of like similar to what we had seen in the tutorial. We essentially have like a DFA, and we want to minimize it with the minimization algorithm. So let's do that. I personally didn't. The table here was a bit confusing to me because I'm used to like the labels being the same. Yeah. So I think that's what I'm gonna do here. But it's also chill if you did it the other way. Okay, so let me write Q0, Q1, Q2, Q3, Q0, Q1, Q2, Q3. And then, so we wanted to first mark the states that were initially distinguishable. So to do that, it's easier to just first determine whether each state is an accept or not an accept state. So in this case, only Q2 is an accept state. Okay. And like I showed you, you only really have to care about like either the lower triangular or the upper triangular part of the table. So so let's do this like this. Okay. So if you look at the sort of pairwise, is it an accept or is it an accept state and not an accept state or vice versa? Then you get something like so Q2 is an accept and then the other ones are not. And then Q1 and Q0 are both not accept, so you're not going to put a 0 there. Q3 and Q2, that also deserves a 0, but nothing else deserves a 0, right? Okay. Then, so that was the first thing. Then the second thing was the recursive case, right? So now I've marked all of the sort of initially distinguishable states. So for the recursive case, I essentially have to look at Q1 with Q0, Q3 with Q0, and Q3 with Q1. Okay, so let's do that. Q1 and Q0, so that's here. When you read an A, you both go to Q1, so that's like no reason for us to mark. Q0 and Q1, when you read a B, you go to Q0, Q2. Q0, Q2, that's marked, right? So that means that I'm going to mark this as well. Then the other one is Q3, Q0. So Q3, Q0, when you read an A, you go to Q1, so no reason to mark. Q0, Q3, when you read B, you go to Q0, Q2, which, like we just said, was marked. So this is another reason to mark. And then lastly, Q3, Q1. Well, Q3, Q1, you can notice that, for A, it's going to Q1 in both cases. And for B, it's going to Q2 in both cases. So like however many iterations you're going to go through, it's always going to be indistinguishable, right? So then the last cell here is going to be the one that we're going to merge, okay? So then if we want to make the actual DFA, it looks like we want to put, let's see, Q1 and Q3 together. And then all the other pairs of states are distinguishable. So then Q0 is going to be alone, and then Q2 is going to be alone. So this is going to be my my start state. Sorry. The accept, these are other states. The accept states are all the states that contain at least one accept state. So in this case, that's just Q2. Just Q2. And then for the transitions, I can just use the transitions from the table. So for Q0, when you have A, you go to Q1. When you have B, you go back to Q0. When you're at Q1, Q3, and you have an A, you go back to Q1, but Q1 and Q3 are in the same thing, so I'll just do that. When you read a B, then you go to Q2. Then for Q2, when you read an A, you go to Q3. So I'll go to like the set that contains Q3. And then when you read a B, you just self loop because you go back to B. Okay. And this was the answer for question 2. Okay, cool. All right. So now question 3. So I'm doing question 2, 3, 4, and then 1. Okay. So question 3, sorry again about the typo here. We wanted to create a DFA that accepted this language, right? So the language that contains sequences of A's, which are whose lengths are modulo 3 equal to 0, but whose lengths modulo 2 are not equal to 0, so then they're equal to 1, right? Okay. And so to do this, we were asked to like build the DFAs of each of these first 2 pieces individually. Okay, so how do I design the DFA for L of AAA whole star? So I just need a cycle, right? I need a 3 cycle where essentially this first state is encoding the fact that my length of my string mod 3 is 0, right? Because like if I have the empty string, then the empty string has 0 A's, so 0 mod 3 is 0. If I have 1 A, then 1 mod 3 is 1. So this is the length mod 3 is 1. And then if I have 2 A's, then the length W mod 3 is 2. And then if I read another A, well, I get 3 A's, but modulo, I just cycle back to being the length of my string mod 3 is 0, right? And then here, the accept state is the state where you have the length of the string mod 3 is 0, right? Because these are like sequences of 3's and 3 A's in a row, right? So you can only have triples of 3's, or you can only have A's that come in groups of 3. So then this is going to be my accept state for this. Okay? Yeah?
If we were to do it using 4 nodes, and we would put the cycle to the second starting node from any node, that makes sense.
I mean, you could do it. Let's see. Yeah, it doesn't have to be minimal. I mean, this would work, but you just have to be careful what the accept states. Yeah, exactly. Yeah. So this and no, this one, right?
Yeah.
Yeah. So this would also work. Yeah. Yeah. But this was this was, I mean, you weren't asked for the minimal one, but yeah, this is the minimal one, right? You can't do it in less than 3 states. It would be impossible. Because you need to encode at least 3 pieces of information. Okay, cool. So then build another DFA that accepts strings over the alphabet A, where those strings have A's in pairs, right? So in that case, I'm just going to create a machine that switches back and forth if you have an even versus an odd number of A's, right? So if I can start right with like 0 A's, so then an even number of A's. If I read an A, then I go from even to odd. If I read another A, then I go from odd to even, right? And what I care about are the strings that look like, the empty string, AA, A4, and so on. So those are all the strings that end here. Right? So that's going to be my accept state. Okay. The third question was to build the product DFA and then use that to create a DFA that accepts the entire language, which again has a typo. Sorry about that. Okay. So how am I going to do this? By the way, I made a video specifically for this question, right? So hopefully you noticed. Yeah. I don't like to waste my students' time. Okay, so I have these two DFAs, right? And I want the product DFA. So how can I use the product DFA? Remember, the product DFA is used for accepting regular languages that look like L1 intersect L2, where L1 is a regular language and L2 is a regular language, right? So we don't quite have that here, but you kind of had to use this trick from set theory, which is that A different B, right? So this is, all of the elements in A that are not in B, but like just saying it sort of in natural language, hopefully that also tells you that it's all the elements in A which are not in B, right? So that means that what I kind of wanted to create a product DFA for was the language L of A star intersect complement of L of A star, right? Okay. So then you had to do one small modification before making the product DFA. Or I mean, you could have made the product DFA and then made the modification. I mean, it's up to you. But the DFA for the language, which is the complement, right? You have to take the initial DFA that accepts the sort of initial language you started with, and then you have to swap the accept and non-accept states, right? Because that gives you the DFA that accepts the complement, right? So then you get a DFA that looks like this, okay? And now I'm going to take the product DFA of this guy with this guy, right? Okay, so how am I going to do this? A useful thing is to maybe name my states. So let's say this is Q0, Q1, Q2. And let's make this S0 and S1. So the product DFA, remember, you take the set of states of each of the machines and you take the cross product, and the transitions are based on where you go from each of the states in the tuples, right? So let's start with the start state. So the start state is always going to be the start state, hello? The start state, we're 4 now, amazing. The start state is going to be the start state of the first machine with the second machine, right? So it's going to be Q0, S0. Then when I read an A, because the only thing I can read is actually an A, when I read an A, well, where do I go when I go from Q0? I go to Q1. And where do I go when I read an A from S0? I go to S1, right? And I'm just going to keep doing this, and at some point I'm going to loop back. So if I read an A from Q1, I'm going to go to Q2. If I read an A from S1, I'm going to go to S0. If I read an A from Q2, then I go back to Q0. But if I read an A from S0, I go to S1, right? Then, okay, I'm back at Q0, and here I'm at S1. If I read an A, I go to S0 here and Q1 here. So I go to Q1, S0. And then if I read another A, how many am I at? Okay. If I read another A, then I go to Q2, S1. And then finally, if I read another A, then I go back to, so if I'm at Q2, right, and I read an A, I go to Q0. And if I'm at S1 and I read an A, I go to S0, right? And so I've actually closed the loop, right? And in fact, if you had done this kind of from scratch, then really the language like for which you wanted to design a DFA was the language something like this, where the length of W mod 3 is 0 and the length of W mod 2 is 1, right? But there's a trick from number theory here where like this is true if and only if, because you have primes, if and only if the length of W mod 6 is, let's see, no, not 1, 3. Yeah, yeah, because 3 mod 2 is odd, and then 3 mod 3 is 0. So then, yeah. So then if we want to look at the accept states, the accept states are the states that are accept states for like Q0, for this machine and this machine. So that's going to be Q0 and S1. So that's just here, right? Okay, and then if you wanted to do this like using this rule, then you would have also made a 6 cycle, and you would have made the third state an accept state, or like the third state reading based on the edges, right? So that works. Okay, cool. Okay, so this was the machine from the product DFA. The next question was, is the language empty? And is it finite or infinite? So this question you could have answered in multiple ways. This is just the way that I sort of thought of when I saw the exam. So to sort of argue that this is not empty, well, you could just say, well, I have a path from the start state to the accept state, to unaccept state, right? So if I have a path, then that means that my machine is going to accept at least one string. So then the language which is accepted by that string cannot be empty, right? So it's not empty, because there exists a path from the start state to an accept state. Okay. And then for finite versus infinite, well, the other thing you can notice is that on the way from the start state to an accept state, there's actually a cycle. I mean, the cycle is at the end, right? So you can end here, or you can also choose to cycle back and end back at the accept state. And you can do this cycle any number of times, right? So then that's one of the reasons why you could, I mean, it's a nice, simple argument for why this is infinite, really. So it's infinite because there exists a cycle on the path from the start state to an accept state, right? And in particular, you basically have like AAA, and then you get to the accept state, and then you can actually cycle with AAA, right? So then that tells you that, you know, you can do this any number of times, right? So your string is going to be infinite. Yeah. Okay.
This is AAA star minus AA star.
Yes.
Then gonna be six.
Oh.
6 is.
Yes. Yeah. Thank you. Because otherwise you get an even number. Yeah. Thanks. Yeah. Yeah. You're right. Because otherwise, if you had like AAA and then AAA, then you would accept like A power 6. But then that's even. So that's. Yeah. No, you didn't have to do this. No, it's cool if it's I mean, hopefully you don't have like here.
Where you put the start date state and I made the end state, and I just added 3 other days as a start state too.
Oh,
I have 9 rows.
you know, I guess string creates
Oh.
a cycle space.
Sure, yeah. I can't actually visualize it that well, but I think it seems like it seems fine. I think, yeah. It doesn't have to be the minimal DFA.
It does the same thing. It has 9 rows.
Yeah, I think if you have like some kind of, yeah, it's fine. Yeah, it's fine. Yeah. Okay, cool. All right. And then there was one last question, which was another reason why I showed you, well, the reason why I showed this in the tutorial was, you know, you want to go from this thing to a regular expression. So you could have used the K-path algorithm. Maybe some of you did. But if I was in your seat, I would have used my method. Well, it's not my method. I didn't invent it. I think it was, no, I don't think it was Stephen Claney. I think it might have been someone else. But okay, so how do you do this? So I'm going to use the state reduction algorithm to convert this to a regular expression. But you could have also used the K-path algorithm. Okay, so let's see. Remember what the goal for the state reduction algorithm is I want to get to something that looks like this, right? And the first step for doing this is you kind of want to, I mean, you didn't really have to do this, but you kind of want to create a new start state and a new accept state with the epsilon transitions. That actually wasn't, yeah, it was probably recommended to do this, but you could have gotten by not doing this, but I'll show you what happens if you do it this way. So I'm going to create, so this is my new start state. And then my new accept state is going to be over here. Okay. And then I'm just going to, read, I'm just going to have the exact same machine, right? So A, A. Okay, and now I'm going to skip a few steps. So really what you could do here is you could eliminate each of these guys right in the middle. I'm just going to skip that step and I'm just going to say, well, this is A, right, as a regular expression. So I'll do that. Actually, I should probably add an extra page. Let's not be greedy. Yeah, so let's do epsilon and then A to here, epsilon, and then A back, right? So I'm also like deleting all of these intermediate states, right? Cool. And then, I mean, you could have either deleted this one or this one. It doesn't really matter. Let's go with, yeah, let's just go with this one. So let's see. If I delete this state, then I have to consider all the transitions that go through it, right? As kind of using the state as an intermediary state. So it seems like I can have like a self loop if I use this state. So in my new machine that doesn't have that state, I should have a self loop, which is, AAA and then AAA, right? So AAA and then AAA. And then the other thing that this is useful for is, epsilon AAA to this stage, right? So then we get AAA to get to this intermediate state, and then we still have this, right? And now at this point, you could just notice that, well, then the regular expression to go from here to here is just this regular expression, any number of times, and then this regular expression. So then we get R is AAA, and then A 6 times, whole star, and then empty string, but then, you can simplify this a bit by just getting rid of the regular expression that denotes the empty string. Okay, and then this is a regular expression. Okay, cool. All right, now the pumping lemma question. So I also I posted a video about something that was kind of similar. So in this question, you essentially have the language L, which is strings over the alphabet AB, where those strings W are not palindromes. W is not a palindrome. And you want to show that this is not regular, right? So it's kind of hard. Yeah, it would have been kind of tricky to find a string and a pumping lemma argument directly for this. I think it's possible, but it would probably have been fairly tricky. So instead, what you can do is kind of like what the hint sort of tells you to do is let's assume for contradiction that L is regular. Well, if we assume this, then that means that, therefore, by the closure properties, L complement, which is strings over the alphabet AB, such that those strings are palindromes, so W is a palindrome. So this language is also regular, right, by the closure properties. So now what I'm going to do is I'm going to use the pumping lemma on this language to show that that's a contradiction. Yeah? Yeah.
But
Yeah. Sorry.
yeah, I had a friend that was like, I really don't know what to do because it said L, not L.
All right. Cool. All right. Okay. So what? Oh, you noticed that? Yeah. Does it seem to the people listening that we cut something out? Okay. So we want to show that this is actually a contradiction, right? That L complement being regular is a contradiction. So we want to show now that L complement is not regular via the pumping lemma. And by the way, there's a question very similar to this in the problem set. If I look up the problem set question, I think it was like, yeah, problem set. So this was in problem set 2. There was a question about like odd length palindromes. So maybe someone had seen, okay, it doesn't look like anyone tried that question, but, oh, nice. Okay, excellent. Great. So then it helped some people. I'm happy. So it's not regular by the pumping lemma. So how are we going to do this? Well, we're just going to have this back and forth argument. You could have also you could have just not done the opponent thing and just sort of written it in standard math. That's also fine. I just like the opponent thing because it's intuitive for people who are less comfortable with these types of proofs. Okay, so how does this go? Well, we start with the for all player. They pick some pumping length P. Now it's our turn to sort of pick a string that has to be an L complement and that has to have length at least P. So you could have picked many strings. A string that kind of works out nicely here is something like AP be AP. Okay, because this is definitely a palindrome. The length of W is 2P plus 1, which is greater or equal to P. And you're kind of like forcing the for all player to pump here, to pick the decomposition here. So then, if you pump up, then you'll get something like P plus K. And then, A, P plus K, B, AP. Backwards, that's not the same string. So then that seems like it's a good choice, right? So then the for all player picks the decomposition W as X, Y, Z. So just because of the way that we pick the string, we get something like this. We have PAs and then B and then PAs. And then the XYs, just because the opponent has to follow the rules of the game, has to be within the first PAs. So, you can imagine X and Y are here. And then Y has to be non-empty. Right? So that kind of implies that Y is A power K for K between 1 and P. Okay, and then I can just pump up or down, actually. It wouldn't have mattered. So let's just pick. The only pump that would not have worked is I is equal to 1. So hopefully I is equal to 1, because then that's just this initial string. So hopefully no one picked that. And if you did, no worries, you'll still get part marks. So it's not that big of a deal. Okay, so I is equal to 2. What happens? I take KAs and I inject some extra KAs in here, right? So you can imagine there's like an extra Y here. So instead of W2 being A, P, B, A, P, I have AP plus K, right? And so so at this point, I think it's probably fine if you just say is not in L complement, but I think the more convincing thing to show is maybe, W2 is PAs and then KAs and then B and then PAs. But then W2 reverse, well, that's PAs and then B and then some other stuff. But then you can already see there's a mismatch here, right? And this is like specifically because K has to be at least 1, right? So then there's a mismatch. W2 is not equal to W2 reverse, which implies that indeed W2 is not in L complement. Okay, cool. All right, nice. Then the last thing is maybe just true-false questions. So the true-false questions, for every regular language, there exists at least one DFA that accepts it. This is true by definition. When reading an input string W, a non-deterministic finite automaton accepts W as soon as it reaches an accept state. So the problem with this statement is it says as soon, right? So like if you have some NFA that looks like this, right? But then you have the string AA, right? Then, where's the pointer? Then, you know, the NFA reads this first string, it gets to the accept state, and then it tries to read the second string, the second letter, and then it can't, right? So then it like jams. So basically at this point, it jams. And when it jams, it means that it does not accept, right? So, and in practice, right, remember like what's going on in an actual DFA, right? Because the DFA is the thing that's actually implementing this. In the DFA, this goes to like a dead state, right? So it wouldn't make sense for the NFA to say, oh, I accept, right? So that means that this is false, right? Okay. Then every regular language has a unique minimal DFA that accepts it. I said this many times in the tutorial 4. I said this like 3-4 times. So hopefully you circle true. Did you see a proof for this? No, right? Because you need the Myhill-Nerode theorem to prove. Yeah, but I think you definitely need this theorem to prove that it's unique. And I don't think Jérôme talks about this theorem. But in case you're interested, I have some YouTube videos.
You didn't say that in the you said that assume that there is another DFA with more states, and then you reach a contradiction at some point.
Yeah, but no, yeah. I guess that kind of works, but I guess that kind of works. If you prove the correctness of the, if you prove the correctness of the minimization algorithm, I think, because I remember talking to Prakash about that argument, and he found a flaw. So, and if Prakash found a flaw, then that means there was probably a flaw. Fair, right? Yeah. Okay. Then question D. This was probably, in my opinion, this was probably the trickiest question of the midterm. In my opinion. Okay. So, because there's a question like in the problem set that says, and I had posted some very quick solutions. So like if you take a regular language and you apply the prefix operator, the resulting language is still regular. And you can actually design a DFA where you just say all the accept states are all the states for which you're on your way to an accept state. Like that's how you actually design the DFA for that. But that doesn't necessarily mean, right, that like prefix of any language is going to be regular. So the prefix of some regular languages, the prefix of some non-regular languages is going to be a regular. So for instance, if you had prefix of this language, or like, this language, or prefix of AP where P is prime, well, this like is just going to give you L of A star, right? Because the primes are unbounded. Okay, so this is true, right? But let's think a bit more about prefix of A and Bn. Okay, so that's a prefix of A and Bn. So what are the possible prefixes of A and Bn? So, you know, I have my string, I have a bunch of A's, and then a bunch of B's. So namely, I have NAs and then NBs. So the prefixes of the strings in this language are, you know, I mean, A and Bn for one, right? And then things like A, so I have A and Bn is a prefix of itself. And then I also have things like AN BM, right? Where I have that, let's see, M is less than or equal to N, right? And then I also have things like just a bunch of A's, right? Okay. So the problem with this is I still have like So this is definitely, if it was just that prefix of a and bn give you this, then you would be good. But the thing is, you still have this, right? So if you see a b, then you kind of have to remember that you can't see more than the number of a's you just saw. So that kind of requires some memory. You can give a pumping lemma argument for this. In fact, you could maybe do like, so it's not so obvious because you have something like, so this language is going to be something like a n bm, where m is less than or equal to n, union an, something like this, right? So this is a bit hard to do. I mean, it's not super clean to do the pumping lemma on this. So you can like intersect it with a star, b star. Like you suppose that this is regular, then the intersection should also be regular. And then you can do the pumping lemma argument on this, right? So then that means that this whole thing is not regular, okay? So then this is false, okay? Okay, and then the last question was the language an, where n is not a prime number, is regular. This was just forcing you to notice like the closure properties, because we know from the problem set, and also he did this in class, that this language is not regular, okay? So then it's impossible that a language is not regular, but then that its complement is regular. Why? Because you could take the complement and complement it again and get the initial language. And then that would mean that you have a contradiction, right? So then again, it's false that this is regular, okay? And then this is how you, these are the solutions. Yeah? This one? Yeah? Okay.
If someone misread the question,
Yeah, totally possible. Yeah.
basically asking to prove that where W is a palindrome is not regular.
Mm.
They used the complement of that.
So you did so hypothetically someone did the pumping lemma on the.
But it's basically the equivalent of proving it with the S where you.
What did you pick as your? What did this hypothetical person pick as their string?
Can I write?
I think we can maybe show. Should we stop the recording? Yeah. Okay. Okay. So hopefully for the people who are watching this, this was informative, and yeah. See you next time.